Hello and welcome to the first video of the FP1 chapter Numerical Solutions to Equations. On the screen as usual is a starter question to get you ready for this video. Pause the video now if you've got time and give this a go. The first one, we just need to evaluate this function at x equals 2. So we go ahead and put 2 into this expression, and if you put that on your calculator you should get 16.1. to 3 significant figures. For part B, we need to differentiate this. That gives us 9x squared. 4 over x, remember, is written as 4x to the minus 1 in index form. That's minus 4x minus 2. And root x is x to the power half in index form. So that becomes minus 7 over 2 x to the minus half. And if you evaluate that expression at 0.5, put 0.5 in for all of the x's there on your calculator, you should find that that is minus 18.7 to 3 significant figures. Next one, part of the graph of f of x is shown in the diagram here. How many roots does this imply the equation to have? Or remember, roots are where the graph crosses the x-axis, so it appears to have 2 roots. I say appears because we can't guarantee beyond the axis this way and this way that the graph doesn't come back down. I can tell you it doesn't, but you'll have to trust me on that unless you put this into a graphing app for yourself. So there are 2 roots implied because it crosses the axis twice. An overview of the chapter. In this video we are going to talk about locating roots using a change of sign. Then in the next 3 videos we're going to do the same thing 3 different ways, and that is to find a root to the required accuracy, first using interval bisection, then linear interpolation, and then something called the Newton-Raphson method. But first let's look at this change of sign idea. So you know already a root of a function f of x is where f of x is equal to 0. And graphically, as I said on the starter, this is where it crosses the x-axis. Now the whole idea of this change of sign thing is that if your function is continuous, so there's no break or jump in it, and it goes from a positive value for the function to a negative value, or from a negative value of the function to a positive value, then obviously it must go through the value 0. It must cross the axis. And this is true for any continuous function, so one that isn't jumping around. And we use this idea, we say it slightly differently, but it's the same idea. We say this: if f of x is continuous, and there is a change of sign, this is the key phrase that you need to know, from f of a, the function evaluated at x equals a, to f of b, the function evaluated at another point, x equals b. So if there's a change of sign from one point to the next, then there must be at least one root, alpha, where alpha is between a and b. So what it's saying is if you evaluate the function, let's say at 1, here that would give us a negative answer, and then evaluate it again at 2, that would give us a positive answer. So going from a negative value to a positive value, if it's continuous, it must cross the axis somewhere. So we know that there must be a root between x equals 1 and x equals 2. That's the idea. And it might seem really obvious, but it's quite useful. Here's an example. The graph shows part of the function this. How many real roots does this function have? Now it's a cubic, and in a previous chapter we looked at different roots a cubic could have. Either it has 1 real root and a complex conjugate pair, or it has 3 real roots, and we can see very clearly from the graph it crosses the axis 3 times, so it has 3 real roots. Part B, verify that one of the roots is in the interval from 4.1 to 4.2. Now it looks about right, it looks like it's this one here, but unless I can zoom in on my graph a little bit, I can't be absolutely sure just by looking at the graph that this is true. So what we do is we evaluate the function at the given value 4.1, and we find out what that answer is. And if you put that on your calculator, you'll get the value minus 0.829, which is maybe around about here somewhere. Then we evaluate the other one, 4.2, see what that is. If you put that on your calculator, you should get 0.488, and that is about here. And the key idea here, the key phrase to use is change of sign of f of x. So there must be a root in the interval 4.1 to 4.2. And we know that for sure because cubic equations are continuous. Again, for your exam situation, this is the key phrase here that the examiner will want to see. But there are some things to be careful of. Firstly, if you only have the change of sign and you don't have a graph, you cannot be sure how many roots are in that interval. You only know that there is at least one root. And the idea here is, if you evaluate minus 2 here, say, and then you evaluate at minus 1.5, you can see that there's a root there, and there'll be a change of sign there as well. But if you choose an interval that's too big compared to the scale of your graph, where the roots are, let's say you evaluate at minus 2, you find it's negative. You evaluate at 1, you find it's positive, and you say, oh, there must be a root between minus 2 and 1, and that's true. But it doesn't tell you that there are 3 roots. All it's telling you for sure is that you're going from a negative value of the function to a positive value, so you have crossed the x-axis. How many times you cross it, of course, depends on the function. In a similar way, you need to be very careful if you don't see a change of sign and you don't have access to the graph. You can't be sure that that means there are known roots, because it might mean that there's an even number of roots. Let's take this graph here again for an example. If you look at minus 2, you get a negative answer. If you look at 0, you get another negative answer. And you might imply, oh, there are no roots there, it's on the same side. But actually what's happened is it's crossed over and then it's crossed back, and you end up with 2 roots. So both of these things are saying, be careful. A sketch of the graph is a very useful thing to have alongside a change of sign, because the change of sign alone is not really specific to how many roots are involved. Finally, remember, this only applies to continuous functions or continuous parts of functions. If you've got something that's got a vertical asymptote, for example, something like this, you might evaluate it here, find a negative answer, evaluate it here, find a positive answer, and say, oh, it must have crossed the x-axis, but in this case it's not true because it continues down here forever negative. Then you have an asymptote, and then it's up here. So there is no root in between there. Another graph you know with a vertical asymptote is the tan graph. So if you've got a 1 over x graph or a tan of x graph, you need to be very careful because these both involve vertical asymptotes. And that's not to say you can't use this idea with these functions. You just need to be that bit more careful about whether or not the interval you're looking at has an asymptote within it. Effectively what I'm saying is, even more than these 2 points, this one is very important to have access to a sketch of the graph to help you, or some foreknowledge of the function as to where exactly those asymptotes are. Another example that you probably won't come across is something like this, which is obviously not continuous. Change of sign from here positive to here negative. Obviously there's no root here because it just jumps across. So this only applies to continuous functions or to the parts of a function that are continuous. Very easy to make a mistake here. Be careful of this. Final example, the graph shows part of the function this cubic equation. A student writes that the function evaluated at minus 0.5 and 0 are both positive, so the function has no roots in the interval minus 0.5 to 0. Now we can't be sure from the graph. I've deliberately taken the x-axis scale off. What we need to do instead is calculate this and explain why the student is incorrect by referring to the diagram here. So I'll get rid of part B for a second to give me space to write. But if we calculate the function at minus 0.5, we get the answer 0.35. Now it's going to be hard for me to put this exact on the diagram, but there is a clear place where it needs to go. If the x value is negative, it needs to be left of this point. And I can see very clearly that all the values from here to here are less than 0.2. So 0.35 must be somewhere in this area. Let me put it around about here. Now I need to evaluate f of 0. That's a little bit easier. That's 0.1. And I can see that that is here. Now, referring to the diagram, we can say for sure that the student is wrong in saying that there are no roots, because we can see between these 2 points there are 2 roots. Part B, calculate the function at negative 0.6 and negative 0.1 and use all your results to show that there must be at least 3 roots in the interval negative 0.6 to 0. So we already had f of minus 0.5, that was 0.35. And f of 0, that was 0.1. So we also need f of minus 0.6, and if you put that into your calculator, you should get minus 1.46, and we need f of minus 0.1. And if you put that on your calculator, you get minus 0.01. So we have our 4 values here. So at f is minus 0.6, we get a negative answer, that's down here somewhere. At minus 0.5 we get the positive answer, that's either here or more likely we can see now it's probably over here. F of minus 0.1 is down here somewhere, and f of 0 again is here. But again, the key idea is the change of sign. From minus 0.6 to minus 0.5 we go from negative to positive. So there must be a root between these 2 values. There's at least one root in there. And then from minus 0.5 to minus 0.1, it changes sign again. So there must be at least one root in here. And then from minus 0.1 to 0, it changes sign again, so there must be at least one root in there. Putting this together, there must be at least 3 roots from minus 0.6 to 0. And of course that agrees with what we see on the graph, and suggests that minus 0.6 is to the left of this point here. And that's quite a short video, but it should give you enough to have a go at the questions from exercise 3a, and in the next 3 videos we'll look at finding these roots a little bit more accurately. Maybe I'll see you in the next video.